Special right triangles are nice little patterns that always hold true that we can use so we don't have to use Pythagorean theorem. If we use Pythagorean theorem, we need to know two sides to find the third. With these special rules, we don't need to know two sides. In fact, we can just know one side. And the reason we can do that is because of these rules. Now, I'm not going to actually go through and derive how these formulas work, but if I have this 45, 45, 90 triangle, meaning that these two angles here are 45 degrees, and the third angle is a 90-degree angle, making it a right triangle, this makes it an isosceles triangle. So these two sides must be the same measure. We'll call it n. No matter what the value of n is, this hypotenuse is always going to be n times the square root of 2. So if n is 5, this hypotenuse is 5 square root of 2. That's it. So it's really just a matter of matching. And we do get a little bit more difficult as we go on, such as this problem. Here we can see that this leg is 5 root 3. And this angle is 45 degrees. Because this one angle is 45 degrees and it's a right triangle, we know that this other angle is 45 degrees, making it an isosceles triangle. Isosceles triangles have equal angles and equal sides. So, or 2 out of the 3 sides are going to be equal. So this is 5 root 3. This side is also going to be 5 root 3. Now, we have to find the hypotenuse. We could use Pythagorean theorem since I have both sides here. So square this, take the square root, and get this hypotenuse. But that's kind of tedious. We can just follow this rule. We know that this side is going to be n root 2. So u is going to be equal to n times the square root of 2. Well, n, we know, is 5 square root of 3. So if we multiply that by square root of 2, we should get the measurement. Now 5 is 5, and if we take the square root of 3 and multiply it by the square root of 2, we're going to get the square root of 6. We can't multiply that by 5 because it's not the square root of 5. They're from two different worlds. We can't combine them. So that's more of an algebra piece. But the concept of the 45, 45, 90 triangle should make sense. If we have these two sides as n, we take that and multiply it by the square root of 2 to get the hypotenuse. The other special case is a 30, 60, 90 triangle. So that's where the angles are 30 degrees, 60 degrees, and 90 degrees. The side that's opposite of 30 degrees, we're going to call that n. The side, or the hypotenuse, is going to be double that, and the side that's opposite 60 degrees is going to be n squared root of 3. So for example, if n were 5, 2 times n would be 10 for the hypotenuse, and the remaining side would be 5 root 3. Again, we can't multiply a number that isn't a square root and that's not a square root. So we just leave it as 5 root 3. So here, first off, we have to figure out which side this is, because this is, upside down. Well, if this angle is 30, this is 90, that means that this is 60. Well, the side that's opposite of the 60-degree angle is n root 3. So we know that n root 3 is going to be the same as this side here. And that's 7 root 3 over 2. Now this kind of looks weird, so I'm going to actually rewrite that, and it might make more sense. Because 7 times square root of 3 divided by 2, that's the same thing as 7 halves times the square root of 3. Now if we have n times the square root of 3 equals 7 halves times square root of 3, n must equal 7 halves. If we can't gather that, we can divide both sides by square root of 3 to isolate n. We get that n is equal to 7 halves. So again, if this side, which is n root 3, is equal to 7 root 3 over 2, that means that n is 7 halves. So the side that's opposite of 30 degrees is going to measure n. So that right here is this measurement there. The side that's opposite 30 degrees is equal to that n value. And the hypotenuse, that's going to be 2 times n. So right here, x, that's 2 times n. So we get 2 times 7 halves, which is equal to 7. So x is equal to 7. And that's it. It's just a matter of setting up some equations and identifying which sides correspond to these special cases for special triangles.